Okay, section 6.1, we're going to begin our work with polygons, and this is the polygon angle sum theorems. There's a few of them that we're going to look at. So, polygon is a closed plane figure formed by 3 or more segments. So let me get it better. So any polygon that has segments that join together, there can be as many as you want. This would have 5. So where the endpoints of each side, the dots that I'm putting in right now, these are the vertices. The diagonal is a segment that connects 2 non-consecutive vertices. So I've drawn the sides in white, the vertices I've put dots. The diagonals connect 2 non-adjacent vertices, so those would be diagonals. That would be a diagonal. That would be a diagonal. And that would be a diagonal. So connecting, in this case, each vertex with 2 other vertices. Since there's 5 altogether, if I start at this vertex, that one is adjacent, so I can't use it. This one is adjacent, so I can't use it, or consecutive. So I need to use these 2 vertices that are opposite, and I have 2 diagonals from that particular vertex. A convex polygon is a polygon where no diagonal contains points outside. So that's a polygon. Again, I did 5-sided again, where all of the diagonals stay inside the polygon. A concave polygon is a polygon where at least one diagonal contains points outside. Concave means that the sides of the polygon go in, so that at least one of the diagonals, in this case this one, that's also a diagonal, that's a diagonal, that's a diagonal. So those are 3 diagonals from this vertex. This diagonal, this vertex has some diagonals. Okay? And some of those diagonals have points outside of the polygon, outside of the area of the polygon. So that's concave. Think of it as convex, that all of the sides and angles go the same direction, containing everything within, whereas concave has some going wonky different ways like that. Okay? Polygons. Special names for polygons. We all know triangle has 3 sides. Quadrilateral is a 4-sided polygon. Pentagon, hexagon, heptagon, octagon, nonagon, decagon. Those are the ones that you need to know by name. After that, we'll just say it's an n-gon. So something that has 12 sides is a 12-gon. Okay, something with 27 sides is a 27-gon. But up to 10, you should know the special name. So take a minute and write that down. Okay, we're now going to try something here. I want you to get rid of that. Oh, come on. I want you to sketch a convex pentagon. Convex, remember again, is the kind where all the sides go the same direction, nothing sticking in. Sketch a convex pentagon, hexagon, and heptagon. Draw all the diagonals you can from one vertex. What conjecture can you make about the relationship between the number of sides of a polygon and the number of triangles formed by the diagonals from one vertex? So turn off the computer, or turn off the video for a minute. Sketch a convex pentagon. I'll get you started on this one. Pentagon is 5 sides. Okay? And from one vertex, draw all the diagonals you can. From this vertex, I can draw 2 diagonals, and that forms 3 triangles. Do the same with a hexagon, 6 sides, and a heptagon, 7 sides. Okay, 6 sides. 1, 2, 3, 4, 5, 6. I'm going to pick a vertex again, draw as many diagonals as I can, and count the triangles. 7 sides. 1, 2, 3, 4, 5. 6. Nope, that's going to be concave. I need to make this bigger. There we go. I think I've got it now. 1, 2, 3, 4, 5, 6, 7. Pick a vertex. 1, 2, 3, 4 diagonals, which means 1, 2, 3, 4, 5. So, 5 sides, 3 triangles. 6 sides, 4 triangles. 7 sides, 5 triangles. So what's our conjecture? Hopefully you can see that the number of sides of a polygon forms 2 less triangles than the number of sides. So if you have n sides, you have n minus 2 triangles. Okay, so let's see what we're going to do to use that. Theorem 6.1, polygon angle sum theorem. The sum of the measures of the interior angles of an n-gon is n minus 2 times 180. So let's start with a 5-sided again. It's a pretty good one to use. And I take my 3 triangles. So I know that the sum of these 3 angles has to be 180. I know that the sum of these 3 angles has to be 180. And I know that the sum of these 3 angles has to be 180. And if I add up all of those angle measures, so this one plus those 2 together, plus those 2 together, plus that one, plus those 3 together, that will equal the sum of 3 triangles times 180. So 5 sides, 5 minus 2 is 3 times 180. So the sum of the interior angles of a pentagon is 3 times 180, which is 3 times 8 is 24, which is 540 degrees. So using the formula, find the sum of the interior angles of a heptagon. A heptagon has 7 sides. So 7 minus 2 times 180 equals 5 times 180, which is 900 degrees. Okay? The corollary to the theorem. A regular polygon is a polygon that is both equilateral and equiangular. Its center is the point that is equidistant from the vertices. So again, I could draw any old pentagon, but it's not regular. The angle measures are different. We can see that this one's bigger than this one. The side lengths are different. But if I can draw a perfectly regular polygon where all of the sides are the same length and all of the angles are the same length, then the measure of each individual interior angle is the measure of all of the angles divided by the number of sides. So both of these have 5 minus 2 times 180, which again was our 540 degrees. That's the total angles, total of all the angles. But a regular pentagon, each angle is our 540, the same thing, divided by 5, or 108 is the measure of each angle in a regular pentagon. Oops. I'm trying to get it to erase. It's not doing it for me. Well, that's okay. All right, each angle. So 180 is the measure of each angle in a regular polygon that has a total of 540 for all the angles combined. We'll do a couple of these in class. Let's try this one. Find the measure of the missing angle. So first I have to count how many sides. 1, 2, 3, 4, again a pentagon. 1, 2, 3, 4, 5 sides. So n minus 2 times 180 is the sum of all the angles. So we already saw that that was 3 times 180, which is 540. So find the measure of the missing angle, x. Well, I know that all of the other angles, 90 for the right angle, plus 110, plus 120, plus 150, plus my x, has to equal 540 degrees. If I add all these up, I get 470 plus x equals 540. Subtracting 470 from both sides, x equals 70 degrees. So that's one way that we can apply the theorem to find a missing angle in a polygon. Our last theorem is theorem 6.2, which is the exterior angle sum. The sum of the measures of the exterior angles of a polygon, one at each vertex, is always 360. No matter how many sides you have, always 360. Let's go back. Well, pause this and write this down. All right, let's go back to our last diagram. So I'm going to use a different color ink, and I'm going to draw some exterior angles. So I'm going to draw this one here. I'm going to draw this one here, this one here, this one here, and this one here. Now, we already figured out that this missing angle was 70 degrees. So I'm going to go and put in place of that, I'm going to put, we'll say that this equals 70 degrees. Pause the video and find each measure of these exterior angles. Remember, you've got a lot of linear pairs here. Okay, so let's see. 150 and 180, this is 30 degrees. Measure of 1 is 110 degrees. 70 plus 110 is 180. Angle 2 is going to be 70 degrees. Angle 3 is 90 degrees. And angle 4 is 60 degrees. If I add those up, 90 plus 60 plus 30 plus 110 plus 70, I'm going to get 90 plus 90 is 180. 110 plus 70 is another 180, 360 degrees. So we'll try a few more of these, but the point is that no matter how many sides you have, the sum of the measures of the exterior angles is always 360. And that's it.